When students walk into our classrooms, they're not blank slates. They bring with them ideas and experiences that shape how they make sense of new information. Sometimes our students' prior experiences and the ways they understand them make it challenging for them to learn the concepts and techniques we want to teach them. Let's see how this plays out in an example from one of my courses, an Introduction to Probability and Statistics. Pretty early in the semester, I posed to my students a multiple choice question, one that I'll now pose to you. Your sister calls to say she's having twins. Which of the following is more likely? Assume that she's not having identical twins. Is it more likely that she'll have twin boys, twin girls, one boy and one girl, or are all three of those equally likely? Take a minute or two to think about this question and submit your answer when you're ready. When I ask this question in my stats class, I have my students answer using a classroom response system of some kind. Each student has a handheld device, often called a clicker, with which they can respond A, B, C, or D. The system tallies their votes and presents the results as a bar graph on the screen at the front of the room. I don't know how you answered, but typically, my students' responses look something like this. Most of the students are split between one boy and one girl, and all are equally likely. I'll show them the bar graph, showing the split, then have them pair up and discuss the question, then vote again using their clickers. The distribution of answers will usually change a little, then I'll ask a few students from each camp to explain their reasoning to the whole class. We hear from the one boy and one girl proponents, and we hear from the all are equally likely voters. Then we run a simulation. I ask each student to take out a coin and flip it twice, heads for boys, tails for girls. I ask the students to report their results using their clickers, and we get a bar graph something like this. At this point, it's pretty clear that the three possible outcomes aren't all equally likely. In fact, the most likely outcome is that you'll have one boy and one girl. You can think of the problem this way. There's a twin 1, who is either a boy or a girl, and then there's a twin 2, also either a boy or a girl. Let's assume, since this is a math class, and we often make simplifying assumptions in math classes, that we are only considering two sexes, male and female, and that each of them occurs in the population with equal probability. Then, putting twin 1 and twin 2 together, we have 4 possible equally likely outcomes: boy-boy, boy-girl, girl-boy, or girl-girl. Each of those outcomes has a 25% chance of occurring, but 2 of them are grouped together under one boy and one girl. That means that there's a 50% chance of having one of each, thus the results of the simulation. Between the simulation and the explanation, most of my students are convinced at this point that these 3 outcomes aren't equally likely. I'm hoping that you're convinced of that now too. The point of this whole sequence of activities is to surface and address a very common misconception, that when you have an experiment of some sort with multiple possible outcomes, all of those outcomes are equally likely. We all have experiences where this is true, which is why so many people have this misconception. When you roll a die and get a number between 1 and 6, each of those numbers is equally likely. When you shuffle a deck of cards and take a card from the top, each card is equally likely to be there. But equally likely outcomes, that's not true in general. My students need to get past this all are equally likely misconception very early in this probability course. Otherwise, they're going to have a lot of problems going forward. That's why I asked them this question and spent a good 20 minutes of class time working through it with them. I have to help them deal with this misconception before they can make sense of the rest of the material. The misconceptions that students have are based on their mental models of how the world works. Back in college, I was fortunate enough to spend 6 weeks studying in London. I grew up in the United States where cars drive on the right side of the road. In London, cars drive on the left. That meant that as a pedestrian crossing the street, I was always looking the wrong direction to see if there were cars coming. Thankfully, the streets of central London have the helpful signs that you see here, reminding pedestrians which way they should look. I'm pretty sure these signs saved my life once or twice while I was there. I came to London with a mental model of how the world of traffic works, a mental model based on my prior experiences. But that mental model didn't describe the world of traffic I found myself in. In a similar way, Our students bring to our classrooms their own mental models of our content areas, probability, forces in motion, chemical reactions, and so on. When those mental models are inaccurate, students have trouble making sense of new information. They'll try to slot the new information into their existing, incorrect mental model. If you've graded student tests or problem sets, you've probably seen the results. Students will say things that don't make a bit of sense to someone with expertise in the area. They're trying to reconcile what they're learning with an existing flaw in their mental model, and it just doesn't work.